equilibrium. And this is just the introduction of equilibrium, so I'll just put here introduction. And simply put, it's the rate of the forward reaction. So I'll just put forward for FWD, rate of the forward reaction as being equal to the rate of the reverse reaction. Now there are a few other points like this that are factors in equilibrium systems, but we'll have a look at that a little bit shortly later in this video. I just want to emphasize here that in stoichiometry, you've kind of been misled in your previous grade in chemistry, and I'll explain why. In stoichiometry, to make the product, okay, so to make the product, you have been led to believe that what limits how much product can be formed is solely based on one factor. Okay, and that factor here is going to be the limiting reagent. That's probably what you've learned. Okay, let's put limiting here as LIM based on the limiting reagent. So if the limiting reagent runs out, you have no more product that can be formed. However, we can never assume, here I'll just put this in stars here, we can never assume the reactants becoming the products will always go to completion. It's not always going to be the case. Let me give you a particular example in case you're a little bit confused here. The rate of the concentration of products. So for concentration, I'm just going to put a bracket here. You should know that this means concentration. So the rate of concentration of products, and same thing for the concentration of reactants. Let's say they are equally going in opposite directions. What do you think is going to happen to the overall change in the concentration of the reactants and the products? Okay, what do you think will happen if the rate of these are equally going in opposite directions? Can still have no change in overall concentration. Concentration of products and reactants. Let me give you an illustration how this works out. We have this person playing tug of war with this person. They are pulling a particular amount of force in their direction to win. So this person is pulling it to the left, sorry, to the right. This person is pulling it to the left. And they're going in equally opposite directions. However, there is no overall change in these products or the reactants. Now, this person over here could pull it a little bit more to the right initially at the beginning. Let's say they have a better founded ground to, have a base of support, or their reflex is a little bit faster after the referee said go. So it pulls a little bit more to the right initially, okay? But eventually, it's going to be at a standstill where this rope is going to look static from someone seeing it from far away. Look like it won't be moving. However, obviously, dynamically, molecularly, microscopically, obviously there is a lot of action, okay, that is happening within that rope because they are constantly trying to fight for it to go in that particular direction. This is why I mean that there is no overall change, because it's never going to be that this person continues to pull and the whole change goes in that direction and that person wins, or this person wins. It's never going to be like that. There's no overall change in the concentration, because as soon as that reactants hit that activated threshold, remember this in our graph, let's say it's exothermic, okay? Let's say those reactants over here hit that threshold and are able to go to completion. It's never going to ever be the same with it where there's no longer products, okay? It's going to go backwards as well, because you've created the products, okay? You've hit that point of no return where these reactants, now that you've made, okay, these products over here are always going to play tug of war now, just like these people, okay? It's going to go in this direction and it's going to go in this direction, okay? And it's always going to be the same amount of concentration. It's just going to stay constant, okay? At some point, the rate of the forward and the rate of the reverse are going to be equal, so that there is always going to be at a particular point of equilibrium that it's not going to change. It's not that these concentrations of the products are going to be the only ones left and there's no reactants, or these reactants are only going to be the ones that left and you're never going to have any products because it just decomposed all to the reactant. It's never going to do that, okay? There will always be this fight and pull, and therefore there will be no change in overall concentration. Now, why is this the case? Because reactants can combine at the same rate the products decompose. Okay, once you hit that threshold, like I talked about, it's going to happen at the same rate. This is why this definition here for equilibrium is very important. At that rate, when both are going to be happening at the same rate, just like how in tug of war here, they're eventually gonna hit a standstill of power where the rope is no longer moving. It's because this person starts to pull at a certain point where it's equal to the amount of this person pulling. Now, at equilibrium, when it hits that particular point, this is when the substances stabilize. So maybe I'll put here, therefore, at equilibrium, the substances stabilize. At different concentrations. I want to preface it here that in the bracket, I want to say that it's not equal. Okay? And are constant instead. Why is this point very important here? Like I said, this person may have had a little bit more pull at the very beginning, but eventually at these different concentrations, it's eventually going to hit constant. The amount of forward and reverse rate is going to equalize, so there is always going to be this dynamic shift of pull in that particular area, but that equilibrium concentration, that constant, will not change. It's hit that point where there's a standstill, and it will not change unless you give it some environmental perturbation to change that particular point. Okay, so if these people are, tug of warring at a particular area, maybe let's say it moved a little bit to the right, let's say 0.5 meters, it is just gonna stay like that, okay, towards the right at 0.5 meters, and it's not going to change unless you do something giving external perturbation to these two people to allow it to go a little bit more to the left or make it go more towards the right. Okay, but if it's undisturbed, it is going to stay there. Now this might be a little bit difficult to kind of comprehend by just looking at a tug of war example. So let me give you an illustration where we use actual reactants and use actual products, okay, chemically. Let's have this graph here. And we have concentration here on the y-axis, obviously increases going at the top, and obviously reaction progress or time, okay, and it goes left to right like always. Let's say we put in a closed system where we have, you know, a reactant that starts all the way up there, okay, let's say it is, you know, N2, okay, nitrogen gas, and a little bit lower on, okay, but it's still quite high. We have H2, okay, so hydrogen gas, and those just continue to decrease, okay, just decreases as time progresses, okay. Same thing with this N2, it just decreases as time progresses. Why? Because of course they're going to react, okay, and of course based on the law of conservation of mass, if you have nitrogens and hydrogens on the left side, what are you going to have for the products? You're obviously going to have nitrogens and hydrogens, okay. So when they do react, obviously you're going to get NH3 or nitrogen trihydride or ammonia, so that's going to start forming, okay. So once these combine, there's going to be less of them because they have created products, so now products at 0, okay, but they're eventually going to create the ammonia, so now the ammonia is going to start increasing, okay. So this will be ammonia now, okay. At a certain point, so let's just lengthen this, extend this a little bit more, okay. At a certain point, let's use this little dashed line over here. What do you think this dashed line represents? Because right now it's quite difficult with the tug of war example to see that even though the rope looks static, it's not moving because both of them are very, very strong. It is difficult to see what is happening molecularly, this dynamic equilibrium. Okay, maybe I'll write this here, this dynamic equilibrium. What do I mean by this term? This dynamic equilibrium is happening at this dashed line, okay? Because at this line, the increase or decrease of these substances, okay, of these reactants or these products are not actually changing anymore. But are now at equilibrium. Okay, so these opposing forces are balanced. Okay, this was, you know, the person on the left for the tug of war. This is the person on the right of the tug of war. There is now going to be an equilibrium, okay, where it's shifted a little bit in the beginning, but now it's going to remain constant. There is no longer a change, okay, this increase or decrease of substances. Obviously, this is decreasing, this is increasing because we're making the product. But at this line, you see how they are equalizing. As you can see, they are different concentrations, okay? Different here, different here, different here, but they are constant. It's continuing to go in that direction, that, but that doesn't really look parallel. Just assume that they kind of look as parallel as possible. Obviously, I don't have a ruler with me right now, so assume this are quite similar as being parallel because they are no longer changing. This means that they are now in equilibrium. You see how they're all in different concentrations. As you can see here, concentrations on the y-axis, they're all in different ones. However, they are remaining constant. Okay, so hopefully this makes a lot more sense now. Now, what are the factors in equilibrium systems? So I'll write this here, factors in equilibrium systems. Now, I've already written out one of them up at the top there. Okay, it was this one. The rate forward must equal the rate reverse. Okay, so that this tug of war can hit that equilibrium standstill point where they're no longer moving. Okay, and then next one would be the macroscopic properties are constant. Okay, macroscopic means obviously macro, what you can see with the eye, so macroscopic as opposed to microscopic, right? So macroscopic properties are constant. So for example, color, these are just some examples. So color, you know, pressure, maybe even state. Oh, pH will be a good one. pH, oh, obviously mass. Okay, mass. Okay, these look constant, doesn't look like they're changing, just like how the rope doesn't look like it's changing. But obviously there are a lot of dynamic equilibria that are going involved, being opposed in those different forces, okay, in the left side and towards the right side. Next, it must be in a closed system. Okay, to be considered in equilibrium, just to make sure that there's no matter being lost. Okay, obviously we don't want energy to be lost either, but that's going to be quite different. Okay, so it doesn't have to be, so it doesn't have to be like isolated closed. Okay, so obviously isolated closed means that you're not just losing matter. Okay, you're also not losing matter, and you're not losing energy either. Okay, so this one here is no energy and no matter being lost. Okay, in a closed system, obviously no matter can be lost. Okay, otherwise this won't work out. Because they're just gonna like vaporize and go out into the air. Okay, however, we obviously have some energy that is being lost. Okay, but we consider that negligible, so not a big deal. But obviously this here would be preferred. Next, equilibrium can be in either direction. Obviously there is a tug of war in either direction, left or the right. And I also want to lastly put, changing conditions can alter this equilibrium constant. So changing conditions can alter I guess I'll leave this equilibrium constant a little bit for next time in the next video. Okay, we don't have time for that, but this equilibrium that we've hit at this point over here, changing conditions can actually change where it particularly is right now. Okay, right now it seems like it's going to go like this forever, like this forever, like this forever. Okay, however, we can alter how high this one goes up. So this one might go a little bit up higher here, this one here might go a little bit lower here, a little bit higher here, this one here could also go a little bit higher here, a little bit lower here. It can change, it can go down or it can go up, again based on changing conditions. Okay, so changing conditions can alter it. However, if that goes back into its original position, then the equilibrium will go back to these concentrations from where it's at. Now I just want to put here down at the very bottom, we have an example here of, let's say, calcium oxide. Let's say this here is a solid and you add it with, carbon dioxide gas. And this is going to be a reversible reaction. Obviously this symbol here means that it can go towards the right and it goes towards the left, right? Like I said over here, right? It can be in either direction, the equilibrium. So let's say it makes, calcium carbonate, and this is going to be in solid form. What do we see with the states? Okay, this one here is solid, this one here is gaseous, this one here is solid. So this is obviously a heterogeneous. Okay, it's heterogeneous because we have different states involved. Different states, okay? But if we use, the example that we used kind of up here, right, with N2, okay, which is gaseous, and hydrogen gas, which is gaseous, and this is reversible as well, and it's creating NH3, which is also gaseous. This here is going to be homogeneous because obviously now we have the same states. Next, how can we lose equilibrium? I did say that the concentration can go up and it can go down and be lost due to external perturbation. For example, let's have this little graph here, and let's say it's exothermic here. So obviously this here would be exothermic. Let's say this here would be endothermic. By increasing temperature, thermal energy is obviously going to increase, right? Thermal energy is the addition, the sum of all the kinetic energy of the particles. Okay, so by increasing this temperature, you're obviously going to increase that excitability. You're going to increase the thermal energy, so the thermal energy increases. So what's going to happen in the endothermic reaction? So in the endothermic reaction, it is now going to take energy and it's going to therefore, so I'll just put here, therefore, increase at a faster rate. And this will be vice versa. By decreasing the temperature, the thermal energy is obviously going to decrease. So now it's going to be the opposite, the exothermic reaction, okay, because now it lost energy. Okay, now this one is going to increase at a faster rate. So what I'm trying to tell you here is that temperature plays an absolute part at this equilibrium change. It's actually the only factor that is responsible as being perturbation as an environmental factor that can actually change this equilibrium constant. And we're going to look at equilibrium constant a little bit later on in this in the next video, but just want you to have a preview that it's only temperature. For example, pressure, if there's an increase or decrease, so increase or decrease of pressure, or the addition or the removal of the products or reactants, or the addition or removal of inert gases, all have no effect on this change. Even a catalyst, okay, maybe I'll put this here, even a catalyst has no effect. All it does is reach the equilibrium quicker. Explain why a rope pull competition or a tug of war is similar to chemical equilibrium. Because obviously there is dynamic. There is a dynamic pull between the rope, but it looks static from an observer. Okay, so this is very similar to the reactants and the products combining and decomposing in a static manner. Okay, so when we look at a system, we don't know that these reactants and products are combining and decomposing. Just like how the rope doesn't look like it's actually moving. But if you were to look at it microscopically, there is dynamic pull within the ropes. There is dynamic change with the reactants becoming the product and the product decomposing back into the reactant. During an investigation, the lab partner says that a chemical system is not at equilibrium because the concentration of the reactants and products are not equal. Explain why this statement might be incorrect. Well, we did already look at how it's not that the concentrations have to be equal, it's that the rate of the forward reaction and the rate of the reverse reaction have to be equal. The concentrations can be different. They just have to be constant. Just have to be constant. So the rates of the forward reaction must equal the rate of the reverse. These must stand true. The concentration, however, does not have to be equal. The term dynamic equilibrium literally means balanced change. Explain why this term describes the chemical system in equilibrium. So like the tug of war example that I provided for you, this is happening dynamically. This rope is going towards the left, the rope is going towards the right. In a chemical system, it's the same thing, like we drew out with that chart. Okay, we had these N2s, H2s combining, and then these NH3s being formed. This here also has a tug of war dynamic feel to it as well. These N2s and H2s here are trying to combine to create this NH3. So this is actually going to be decreasing. As you can see, it is going downwards. It is decreasing in order to create this product. But it's not going to keep going down. It's going to remain at a standstill because eventually these products are going to be creating more of these NH3. So you see how this NH3 over here, it's not going to keep going up because it's going to decompose. Okay, it's going to decompose back into this. That's why it continues just to go, a little bit towards, parallel as this one is and as this one is. Okay, so these again are decreasing in order to create this NH3, but they are also increasing as well thanks to this NH3, because this NH3 is decomposing back into this NH2, sorry, this N2 NH2. This NH3, it was increasing because they were being made, okay, thanks to these guys over here, but eventually this NH3 cannot keep going upwards because eventually it's going to help make more of that N2 and H2, hence why you see, this illustration over here. It is dynamically occurring, just we cannot see it. Just like how this here, opposable forces in either direction. We cannot see that the rope is moving, but we know that it is happening. Otherwise, this person would have pulled this person and yanked it towards the right side, or this person would have yanked this person towards the left side, but they're both fighting. So that's why there is a balanced change. Okay, there is change obviously happening, we just can't see it. It is dynamic, we can't see it, it's microscopic. Okay, but of course there is balance. This here is your green question of the day. Give this a try on your own, pause the video, give it a very elaborated answer, and I'll be giving you the answers shortly. This is the answer.